Okay, so I want you to try a little experiment with me. Uh, Imagine you were trying to learn a completely new language,
Okay.
but there is a really annoying rule. You are only allowed to look at one word at a time, and the moment you look at the next word, you have to cover up the one you just read.
Wow. That sounds like a nightmare. You would lose the thread of the sentence almost instantly.
Right. You are forced to hold this massive, growing list of words in your short-term memory, desperately trying not to forget the beginning of the sentence by the time you reach the end. It feels inefficient, stressful, and honestly, kind of human.
It is human, and for decades, that is exactly how we taught artificial intelligence to read.
Step by step, word by word. But today, our mission in this deep dive is to unpack the exact moment researchers looked at that method and said, you know what, no. We are exploring the 2017 paper that basically took the old AI rulebook, set it on fire, and built the foundation for every major AI tool we use today.
Yeah, it is the paper that gave us the modern era of AI. It is titled Attention is All You Need by Ashish Vaswani and his colleagues at Google Brain, Google Research, and the University of Toronto.
Which, I have to say, is just a fantastic title. It sounds less like a dense computer science paper and more like a relationship advice column.
It really does. But they definitely weren't giving relationship advice. They were making a very specific and actually very controversial technical claim at the time.
Let's set the stage for you, the listener, because to understand why this was so controversial, we have to look at the status quo prior to 2017.
Hmm.
If you wanted an AI to process language, you used recurrent neural networks.
Yes, RNNs. Or if you were dealing with more complex tasks, you used long short-term memory networks, or LSTMs, or gated recurrent networks. But they all shared the same fundamental
All
architecture.
right, they were all sequential.
Exactly, they process data in order, just like your one word at a time experiment. If an LSTM sees the sentence, the dog bit the man, it processes generates a hidden state, and then passes that state to help process dog, and then passes that combined state to bit, and so on.
So it generates a hidden state based on the previous state. It is a chain. The understanding of the word man fundamentally relies on the calculation for bit, which relies on dog.
Precisely. And that creates a massive, massive bottleneck. Think about the hardware these companies use. They have thousands of GPUs designed to do math in parallel, to do a million things at once. But the RNN architecture basically says, stop. You have to wait. You cannot process step 2 until step 1 is completely finished.
It's like having a Ferrari and being stuck in a drive-through line.
Yeah.
You have all this power, and you were just idling.
That is a perfect analogy. The inability to parallelize the training was a massive issue, especially as sequence lengths got longer, mostly due to memory constraints. But there was a second problem, which the paper identifies as the distance problem.
The difficulty of learning dependencies between distant positions in a sentence.
Right. Imagine a paragraph that starts with a specific subject, and the verb that applies to it is 50 words later at the end of the paragraph. To understand the relationship, the model has to connect that verb all the way back to the subject.
And in previous models, like convs2s or ByteNet, the number of operations required to relate two signals grows with the distance between them.
Yes. The signal has to travel through all those intermediate steps. It is like a game of telephone. By the time the information gets from the start of the sequence to the end, it is distorted. The gradients vanish. The model effectively forgets earlier context.
So the old guard of AI was bottlenecked because it couldn't parallelize, and it struggled with context because it couldn't handle long distances efficiently.
And that is exactly why attention is all you need was such a paradigm shift. The authors didn't just propose a tweak to make the RNN faster. They proposed a completely new architecture called the transformer.
The transformer completely eschews recurrence. It throws out the sequential processing entirely.
Completely. The fundamental premise is that you do not need recurrence and you do not need convolutions. You just need an attention mechanism to draw global dependencies between the input and the output.
So instead of reading left to right, word by word, the transformer processes the entire sequence at once. It parallelizes everything.
Right. And the immediate benefit is that parallelization. But the second and arguably more important benefit is that the path length between any two positions in the network is reduced to a constant number of operations, O of 1.
Okay, let's unpack that O of 1 for a second. That means the distance between the first word of a sentence and the last word is essentially the same as the distance between two adjacent words.
Exactly. It is always one step away, which makes it infinitely easier to learn long-range dependencies. The subject at the start of the paragraph and the verb at the end are directly connected.
Now, structurally, the paper mentions the transformer still follows a standard encoder-decoder structure, right?
It does. It has an encoder that maps the input symbols to representations, and then a decoder that generates the output symbols one element at a time, which is autoregressive. And both the encoder and decoder are made of stacked layers, 6 identical layers each in the base model they proposed.
Okay, so I get the structure and I get the why. Parallelism gives us speed, and direct connections give us better memory.
Okay.
But let's get into the how. Let's dive deep into how this attention mechanism actually works.
Let's do it. The core concept is self-attention. The paper defines this as an attention mechanism relating different positions of a single sequence to compute a representation of that same sequence.
So the words are looking at each other to figure out what they mean in context. And the paper uses this really specific mathematical framework to explain it. Queries, keys, and values.
Yes, scaled dot product attention. It sounds abstract, but think of it like a retrieval system.
Like a database lookup.
Sort of, yes. Imagine the model is looking at the word bank in a sentence. It needs to know if this is a river bank or a financial bank. So the word bank creates a query. It broadcasts a signal to every other word in the sequence.
Asking for context.
Right. And every other word in the sequence holds a key. The key is a representation of what that word contains.
So the model computes what the paper calls a compatibility function. It takes the dot product of the query with all the keys.
Exactly. The dot product is just measuring how aligned the query and the key are. If they match well, the score is high. If they don't, the score is low.
So if the sentence is, I sat by the river bank, the query from bank aligns really well with the key from river.
Yes. And once it computes those scores, it uses them to weight the values. The value is the actual content of the word. So bank absorbs a lot of the value from river, updating its own representation to mean a nature bank, not a money bank.
Millions of these calculations are happening in parallel. But I want to touch on the scaled part of scaled dot product attention, because I know dot products can result in massive numbers.
They absolutely can, especially when you are dealing with large dimension depths, which this model does. And here's why scaling is so crucial. The scores from the dot products are passed through a softmax function to turn them into probabilities, basically numbers between 0 and 1 that add up to 1.
Right.
But if the dot products are huge, the softmax function gets pushed into regions where the gradients are extremely small.
It pushes it out to the edges.
Exactly. Think of it like a camera lens. If you let way too much light in, the image blows out. It's all just white. You lose the contrast. The model can't distinguish between a good match and a great match because everything is just maxed out.
The gradients vanish, so the model stops learning.
Right. So to counteract this, they scale the dot products. They divide them by the square root of the dimension depth, the square root of d sub k. It's an elegant mathematical trick to keep the values in a range where the softmax function can actually do its job effectively.
It turns down the volume so you can actually hear the nuances in the music.
That is a great way to think about it. But they didn't stop at just one attention mechanism. The secret sauce of the transformer is multi-head attention.
Right, because language is multifaceted. Paying attention to just one set of relationships isn't enough.
Exactly. A word can have a syntactic role, a semantic meaning, a tone. So instead of performing a single attention function, they project the queries, keys, and values 8 times into different, smaller dimensions.
8 different heads operating in parallel.
Yes. A single attention head inhibits the ability to focus on different positions and different representation subspaces. By having 8 heads, the model can jointly attend to information from completely different perspectives simultaneously.
It's like having 8 different pairs of glasses. One pair is looking for grammar, figuring out the subject and the verb. Another pair is looking for vocabulary definitions. Another pair is looking at the emotional tone of the sentence.
And then the results from all 8 heads are concatenated, they are glued together, and projected once more to create the final representation. It gives the model an incredibly rich understanding of the text.
Okay, so the attention mechanism is incredibly powerful. But as we research this, there's a glaring missing piece when you throw out recurrence.
Positional information.
Right. Because if you process everything at once, in parallel, without a sequence, you just have a word soup.
Mm-hmm.
To the model, the dog bit the man, and the man bit the dog, look exactly the same mathematically if you don't know the order of the words.
It is the biggest hurdle of dispensing with the RNN. Since there is no step 1, then step 2, the model has absolutely no inherent way to know the sequence order.
So they had to inject the order back into the input. They used positional encodings.
Yes, they add these positional encodings directly to the input embeddings at the bottom of both the encoder and decoder stacks.
Now, a naive approach would just be to number the words. Word 1 gets a 1, word 2 gets a 2, but they didn't do that.
No, simple integers are problematic. What if you train on sequences of 50 words and then in the real world you encounter a sequence of 100 words? The model has never seen the positional encoding for position 99. It wouldn't know what to do.
So they needed a method that scales and extrapolates. The paper details that they used sine and cosine functions of different frequencies.
Right. The wavelengths form a geometric progression from 2 pi to 10,000 times 2 pi.
Which sounds intense, but essentially they're giving every single position in a sentence a unique, continuous wave signature.
Exactly. They hypothesized this would allow the model to easily learn to attend by relative positions, because any fixed offset can be represented as a linear function of the position.
So it's like a complex timestamp. Even if the model sees a sequence length it is never trained on, the wave functions continue naturally. So the model can easily deduce that word 80 is 5 steps away from word 75 just by looking at the frequencies.
It completely solves the word soup problem without sacrificing the parallelization.
Okay, so we have the architecture, the parallel processing, the multi-head attention, the sine wave positional encodings. The real question is, what were the actual results? Because a cool theory is great, but did it perform?
It blew everything out of the water. The performance section of this paper is incredible, and the most striking thing is the training speed.
Because they finally got rid of the bottleneck.
Right. They trained their base model for just 12 hours on 8 NVIDIA P100 GPUs.
12 hour.
12 hours. And their big model, which was significantly larger, took 3.5 days.
Contrast that with the previous state-of-the-art models like Google's Neural Machine Translation System or ConvS-2S. Those required vastly more computational resources, measured in huge amounts of FLOPs, and took significantly longer to train.
We are talking about reducing training time by an order of magnitude. But it wasn't just fast. The translation quality was unprecedented.
They measured this using BLEU scores, which, for you listening, is a standard metric used to evaluate the quality of machine-translated text against human translations.
Yes. On the English to German translation task, the big transformer achieved a BLEU score of 28.4.
Which beat the existing best results, including massive ensembles of multiple models, by over 2.0 BLEU points.
And in this field, fighting for 1/10 of a point is common. Beating the state-of-the-art by 2 full points with a single model is a massive leap.
And it gets better. On the English to French translation task, it achieved a score of 41.8, establishing a brand new, single model state-of-the-art.
And it did that at less than 1/4 the training cost of the previous leading model.
Faster, cheaper, and vastly superior results. But they didn't just test it on translation, did they? They wanted to prove generalization.
They did. They threw the model at English constituency parsing, which is basically figuring out the grammatical structure of a sentence.
Building a syntax tree.
Right. And even with limited task-specific tuning, the transformer performed surprisingly well, beating out specialized recurrent neural network grammars that were explicitly designed for that exact task.
It proved that attention was a general-purpose tool. Which brings me to one of my favorite parts of the paper, visualizing the black box.
The interpretability aspect.
Yes. Usually, deep learning models are opaque. We feed data in, we get answers out, and we have no idea how the model arrived at the answer. But the authors note that self-attention models are inherently more interpretable.
Because you can actually map the attention weights? You can see exactly which words are paying attention to which other words in real time?
The paper includes these fascinating figures 3, 4, and 5, showing exactly this. For example, they show how the model handles long-distance dependencies. In layer 5, the attention heads successfully connect the verb making to the phrase more difficult across a huge span of intervening words.
Something that would have completely lost an old RNN model, but the most impressive example is anaphora resolution.
The pronoun problem.
Right, figuring out what a pronoun refers to. They use the phrase, the law will never be perfect, but its application should be just.
As humans, we know it's refers to the law, but a computer doesn't naturally know that.
But when you look at the attention visualization for the word it's in that sentence, the attention heads are focused sharply and almost exclusively on the word law.
The model independently understood the grammatical reference without ever being explicitly taught the rules of grammar. Just by predicting words and adjusting weights, it learned syntax.
And the visualizations also prove the multi-head theory. Different heads clearly learn to perform different specific tasks. One head might focus entirely on the next word in the sequence, while another head is entirely focused on verbs. It built its own internal organizational structure.
It is genuinely remarkable. So to recap our deep dive for you today, this 2017 paper changed everything by replacing recurrence with attention. It allowed for massive parallelization, dropping training times drastically, and it handled long-range dependencies better than anything before it, leading to record-breaking results.
It unlocked the scale that makes today's large language models possible. You simply could not train a model the size of GPT-4 using sequential processing. The universe would end before it finished.
And the authors were incredibly forward-looking in their conclusion. They explicitly state their excitement about applying this attention-based architecture to input and output modalities other than text.
They specifically name-dropped images, audio, and video. They knew that attention wasn't just about language. It was a fundamental way to process any structured data. Pixels in an image relate to each other the same way words in a sentence do.
And now we are seeing the results of that foresight. AI generating photorealistic video, composing music, analyzing medical scans, it's almost all built on the foundation of the transformer.
It really makes you reflect on the title. Attention is all you need. It was a bold claim, but it turned out to be remarkably prophetic.
It leaves you with a really provocative thought to mull over. We often think of language understanding and human-level reasoning as requiring incredibly complex, rigid, rule-based systems. We assume intelligence is a highly complicated hierarchy of logic.
But if this model can learn the nuances of grammar, like anaphor resolution, simply by paying attention to the right relationships between data points, it suggests something fundamental.
That maybe complex intelligence is actually much simpler than we thought. Maybe it really just boils down to knowing what to focus on and what to ignore. If you pay attention to the right connections, the understanding just emerges on its own.
It's a profound realization.
It really is. Thank you for joining us on this deep dive into the architecture that reshaped the world. We will catch you on the next one.